Okay, everyone, we had to switch down to the basement because we need a little bit more space and we had to be able to move around a little bit more. So we said, thank you, Lucas. And now we moved down to the basement to get more space. So if we look at the one sample t-test, we have to remember the assumptions that we talked about in the previous video, all the different things that we need or the requirements to actually run a t-test. We also have to keep in mind that the one sample t-test also only runs with one sample. So we have to run it using the 4 steps of hypothesis testing. Remember, the 4 steps were: first, you had to state the hypothesis. There were 2. Then you had to set the criteria, which were 3 types of criteria we're going to set: alpha level, critical region, and degrees of freedom, which now we're going to use degrees of freedom within the actual t-test because of the restrictability and the limitation the sample has to ensure that it actually represents its population. We're then also going to look at the actual computing, running the actual t-test using the formula, and we're going to make a decision based off of APA. So to make this a little bit more understandable, I always have to keep in mind the formula itself. So we're not jumping to step 3 because we don't want to do that. We don't want to create confusion, but we do want to keep in mind the formula and what it's doing and what it's testing. So I'm going to put it right here so we can look at it as we're thinking about the different steps. So the t-test, the actual one sample tests one sample. So we have one mean of one sample minus the mu, the population. Then we have the estimated standard error. So now we have from sigma to s, and hopefully we remember this stands for formula, the variance over n, square root the whole thing, or you can do the standard deviation over the square root of n as the bottom of the formula. I prefer this one, but you can do either more because remember, to get the standard deviation, you actually square root the variance. So let's look at an example. If we're going to evaluate the effect size of a weight loss treatment, a sample is obtained from a population that gives a mean of 30. The treatment is administered and a sample of 16 individuals. After treatment, they had a mean that was come out to be 31.3. And they had a standard deviation of S equaled 3. So is the data enough to actually conclude that the weight loss treatment has a significant effect on the actual person's weight in an alpha level of 5% or 0.05? Now, reading the question, you can think about the question being one of 2 things. Weight loss can lead you to think that we're talking about something in the decrease side. That can lead to a one-tailed directional test. Or you can think about the idea they just simply said, does it have an effect on a person's weight? And the effect can actually be an increase in weight or a decrease in weight. So let's look at it first as if it was a 2-tailed test having a significant impact on their weight, which can actually be an increase and not just a decrease. So we're talking about a 2-tailed test. So if we talk about a 2-tailed test, let's pull the information for us first. Like I said, it's always easier to pull information and then run a test than just simply think about it all overall. So if we pull the information, what did we have? We had the mean of the population lost about how many pounds? About 30. And then we had the mean of the sample. The sample was how many? 16. So 16 people, their weight loss came out to be 31.3. And they had a standard deviation, an S, of actually 3. So now that we pulled the information, the last thing we need is our alpha level, which here we're going to use the default of 0.05. All of this information is needed for you to actually run the test. So now that we have to think about the weight loss treatment, let's actually run the test, starting with step 1. We have 2 hypotheses. So then state both of them. We have the HO and the H1. So we have the null hypothesis. Remember, this is a standardized test. So we're not going to put the mean as 30, greater than 30, less than 30. We're going to actually put 0 because when we standardize things, the mean automatically becomes 0. So the 0 theoretically stands for any mean that we're looking at, in this case 30. And we're going to test against the population, never against the sample. So when we actually state our hypotheses, we use mu and not capital M. So mu's. And now if we're looking at this as having an effect, but not, we don't know where, effect increase or weight effect decrease, we're looking at a simple, does it equal 0 or theoretically 30, or does it not equal 0, theoretically 30? So this gives us a not equal, gives us a 2-tailed non-directional test. And that's really important because step 2 has to do with setting your criteria. And the criteria is the alpha level, which we know is 0.05. We need degrees of freedom, because remember, our sample sizes are restricted, which is the sample size minus 1. So we're going to do 16 minus 1. So degrees of freedom is 15. And we also have to think about how many tails we have. Here we have a non-directional, which equals 2 tails. Why do we need all this information? Because if we're actually going to do our T critical, when we think about this, right? We think about our distribution. We're saying that it could be on either side. It can be here or it can be here. We need to know, when does that tail begin? When does the body, the big chunk, end? So what number tells us this is the beginning of our tail on the lower side and this is the beginning of our tail on the higher side? When you go back and look at the T table, because each test has its own table, and you look at the appendix of the T table, just like the Z had the unit normal table, we have the T table. You're going to need all of this information. So if you ever forget how to conduct step 2, just look at the table. All the information you need to actually pull the numbers from the actual table are what you do and set the criteria. So in the table, it'll tell you what's your alpha level. It'll ask you what's your degrees of freedom. And then it'll ask you how many tails you have. And then you can simply read the chart. And when you read the chart, it will give you a T critical value. What is the T critical value? It basically means if you are greater than or less than a particular number, because we have 2 tails, right? Greater than or less than, positive or negative, greater than or less than this particular number, then you are in a tail. You are significantly different. In other words, you demonstrated your alternative hypothesis. So if we were looking at it and we actually pulled the number from the back of the book, it actually, or the back of our table, it actually came out to be 2.131. Never round this number, because if you round the number and get rid of the 1, and what if you got 2.130? Then you would have thought you're in a tail, and you're actually not. You're in the body. So you have to make sure you keep every single one of these values. These are values that you never actually round. So the T critical is 2.131. So you have to be within the 2.131. Negative 2.131, positive 2.131. So if you are bigger than it or you are less than it on either one of these sides, you are in the alternative hypothesis. In other words, you demonstrate that your sample is significantly different than the population itself. So now that we have step 1 and step 2, it makes sense to then run step 3. In other words, pull the information in. What's the mean of our sample? The mean of our sample is 31.30 minus the mean of our population, 30, over the standard deviation is the one that we have in this example, so we don't have to use the variance. We have 3 over the square root of 16. Square root of 16 is 4, so 3/4, and essentially if we're looking at 3/4, 3/4 is 0.75. And what's 31.30 minus 30? 1.3. So 1.3 divided by the 0.075 is going to lead us to a T of 1.73. So, like I said, it makes sense to run all 3 steps and in order, because 1, it's ethical, and 2, it wouldn't make sense if you didn't do it this way. Because if you would have gotten 1.73 without running everything else, what happens to most of my students, they say, Professor, now what do I do? I'm kind of stuck. And then I always ask them, where's your step 1? Where's your step 2? And that's where I kind of get the scratch in the head, or the dodge and weave as I call it. And they say, I didn't do it. And I was like, well, let's go back and do it. When we actually go back and do it, we realize, okay, what were we testing? We were testing that there was an idea of 2 tails, 2 different places. And we were saying that our critical region, our tail began beyond negative or positive 2.131. And now that you ran your T and you got 1.73, where did you land? In HO or in H1? Whose house are you in? Well, 1.73 is inside of the body. It is not greater than 2.131. So is there a significant difference between these 16 people's weight loss in terms of this program? Did they have a significant difference in their weight loss as compared to other programs that are out there that do the same thing, just like Jenny Craig and Oprah and all these other different programs that are out there now that help you with weight loss? In reality, no, this program didn't do anything. So what do you do in your step 4? You do exactly what I just told you. You make a decision, and you're going to write a beautiful paragraph that's going to explain this whole entire process. And at the end of that paragraph, you're going to write T with the degrees of freedom, the actual value that you got. The probability is either greater than or less than the actual alpha level, in this case, 0.05. So if we were to write this out for this problem, what would that look like? At the end of your paragraph, you would essentially have to say this very example. A weight loss treatment was administered to a sample of 16 individuals to determine the effect of the program. The individual reported a higher effect from the weight loss treatment with a mean weight loss of 31.3 and a standard deviation of 3 pounds, which is greater than the general population who had a mean of 30 pounds in terms of its weight loss. Is there significant evidence to determine that this weight loss program had an effect? No. So what would we say? There is not sufficient evidence to determine that this weight loss program had a significant difference in the effect of weight loss for these 16 people. And at the end of that sentence, you would put T, the degrees of freedom here was essentially the sample size minus 1, so 15. Then you would say what our value is, 1.73, and our probability. Whose house are we standing in? Are we standing in the less than 5%, the tail H1's house? Or are we standing in the greater than 5%, 95% HO's house? So we are standing in HO's house. We are standing in the greater than 0.05%. In other words, we are standing in the 95% house, so there is no significant difference between these 16 people and their impact of this weight loss program.